Hello students, welcome to today's lecture on traction inverters in electric motors. Traction inverters are an important part of EV. They control how electrical energy is delivered to the motor, but designing them is not easy. As an engineers, we must balance between efficiency, cost, size, and also the reliability of the entire powertrain. So the challenges include the driver needs faster accelerations, and also the manufacturer wants low cost, and the environment demands high durability. So understanding these challenges is very important while designing a traction inverter. Now let's design what a traction inverter is. A traction inverter converts DC power into AC power, so it supplies power to the motor. It is bidirectional, which means it drives the motor forward power flow and it also supports regenerative braking for energy recovery. And its key factors includes it gives an efficiency above 98% and also power range of 100 to 200 kilowatts, and also it offers high power density. In simple words, we can say it as the brain that controls the motor power. Now let's understand how it works. The inverter uses semiconductor switches like IGBTs or MOSFETs, which are used to on and off which switches on and off at very faster pace, because to convert the available power into the desired power for the motor. For example, if we have a DC power source, then we will need a chopper to convert the DC power into AC power based on the motor type we use. If we use a DC motor, then we need an inverter. If we use a DC motor, we need a chopper circuit. We need an AC motor. We need an inverter switching operations. So here the process is that the battery gives DC power, the inverter converts it into three-phase AC power if it is a AC motors used for AV. If it is a DC motor, we use a chopper circuit, and also which is a DC to DC converter, and also this converted power makes the motor to rotate. So it uses a 6-switch circuit and pulse width modulation technique. For example, like switching a light on and off very fast to control brightness, the same way here we use power semiconductor switches which are on and off in a sequential manner at a very faster switching speed, so that the desired power waveform, AC waveforms, can be obtained from the DC source. Now let's ideate. Let's explore modern inverter techniques. We have many advanced inverter technologies, which includes multi-level inverters, which can be used for smoother output. We have interleaved inverters, which provides high power, and also wide gap devices like silicon carbide, gallium nitride, which provides better performance, and also soft switching will offers less loss. So these technologies improve the efficiency, performance, and also the reliability. So now compare two different materials which are highly used in this making of IGBTs, which is the silicon versus silicon carbide. So this material selections also have a greater impact in traction inverter designs. So silicon offers lower cost and is widely used, but silicon carbide SiC is providing higher efficiency and it is good at working at high temperatures. Also, it provides faster switching. While talking about the trade-offs, silicon carbide is 3 to 5 times costlier, but it improves efficiency, range, and cooling since it has more advantages compared to silicon, and also it is costlier. We make a trade-off here, so it is mainly used in premium EVs. And talking about the thermal management, this heat management is an important aspect in high power converters because a lot of heat is being liberated due to switching. Why cooling is important for inverters is that it prevents damage because these are power electronic devices operated at less power applications. So these heat may damage the entire circuitry. So we need to prevent this damage, and also we need to maintain the performance of the machines. So we need to provide adequate cooling technologies in order to have a proper thermal management. So liquid cooling, which is the most commonly used cooling technique, wherein which water glycol mixture is slow flowing through cold plates, which extracts heat with minimal thermal resistance. And also we use advanced cooling methods like microchannels and direct cooling methods also. How this heat is processed? The heat generator is removed by the coolant and is released through the radiator. So a good cooling will give longer life and better efficiency. So now let's look into the real world inverter designs. A Tesla Model 3 car uses IGBT inverters which provide high efficiency, approximately 98%, and offers compact designs. And a Lucid Air car uses SIC inverters which offers high power of 670 kilowatt with high power density. And GM Ultium platform, which is released in 2022, offers modular inverter design which works for multiple vehicles and also uses cost. So companies designs inverters based on their goals. So now let's understand how we measure inverter performance. So the key metrics for measuring the performance of an inverter are efficiency, power density, and reliability, which is weighted efficiency, volume utilization, that is power density, and the target reliability. So the efficiency should be above 97% and the power density should be 85% and reliability should be 100%. So efficiency varies with operating point, power density impacts the vehicle packaging, and reliability determines the warranty cost and customer satisfactions. And apart from this, certain other factors also being used for power performance matrices, which is efficiency mapping, power to weight ratio, lifetime cost also. So these are also considered while evaluating the traction inverter performance. So at the outset, a good inverter should be efficient, compact, and reliable. So next comes the testing part. Before using in EVs, these inverters undergo strict testing. So the type of testings for validating these inverters are component testing, which is a general thing, wherein which each individual semiconductor, capacitor, gate drivers will be tested with the data sheet specifications, and it is screened for defects. And then subsystem testing, wherein which after integration separate subsystems will be tested, like power stage assembly, and then powertrain, the motor drive configurations, like it is divided into many subsystems and it will be tested. And then full system testings, wherein which the entire operating envelope validates the efficiency, control response, and protection functions. Finally, the environmental testing, wherein which the temperature, vibrations, humidity, salt spray testings, everything will be done in order to ensure the vehicle lifetime across reliability. And finally is the EMC testings, wherein which the electromagnetic compatibility, because the electromagnetic emissions from one device should not have an interference on the neighboring devices. So these EMC compliances needs to be addressed. So radiated and conducted emissions testings will verify these compliances with respect to the EMC standards. So these testings will ensure safety, reliability, and long lifetime operations. Now, let's applying these design thinking principles what we have discussed and learned so far in order to design our own optimal inverter. Okay, so let's do an activity. You need to decide the semiconductor type, cooling method, inverter type, and switching frequencies. Why I have given few specifications here based on which you need to design your own inverter. So while choosing between these every options, you need to think about the cost, performance, and reliability. So the answer for this is that there is no single correct answer because it depends on your design goal. What for applications you are going to use. Based on that, you have to justify your traction inverters. You cannot have a common traction inverter for all kind of EVs. So your designs may vary based on the applications, cost, performance, reliability, and also make sure you make a critical design decisions. So now after designing, you need to have a reflection on your designs. How does your choice affect cost? What testing is required? How will future technology change your design? Whose need did you prioritize? The driver or the manufacturer or the end user or the environment? So this is how real engineers think and design systems. So we have come to the end of this traction inverter session. So let's summarize today's session. We have discussed what is a traction inverter that converts DC to AC. It controls motor performance, so if its efficiency can exceed 98%. And what are the design parameters we need to consider? What are the trade-offs? And how a well-designed inverter improves range, efficiency, and driving experience. These are all the things we have discussed today. So that's all for today's lecture. Thank you for watching. See you in the next class.